Hello everyone, and thank you for joining us for the first episode of our series of conversations with our service analysis team and our customers. The guest we have today collected his first XPS spectrum in 1976, and since then has become prolific with 428 publications to his name, including the second edition of An Introduction to Surface Analysis by XPS and AES. He's been the editor-in-chief of the journal Surface and Interface Analysis for 20 years, and perhaps most importantly, he was my Eng.D supervisor. Professor of Materials in the Department of Mechanical Engineering Sciences at the University of Surrey, Professor John Watts. Hello, John.
Hello, Robin. It's really good to be with you today.
So tell me, how have things been going for you and the university during lockdown?
Well, pretty much we closed the campus for probably 3 months. Towards the middle of June, we started opening up a few labs. I'm pleased to say that the Surface Analysis Lab at Guildford is up and running as of the 1st of July. So we're seeing our students coming in occasionally. We've not got any external customers coming in yet. Some of our users from elsewhere on campus are also coming in. So we're in good shape. Yeah, and because of the lab is pretty large, as you know, social distancing is not an issue. And we were social distancing probably from the beginning of March. So it's really sort of back to where we were sort of some 4 months ago. So we're pretty positive. And although I'm still being told to work from home, I've got permission to be on campus as of this morning when I spoke to the head of the department, as and when I wish. So I can go in from time to time.
Oh, good news. Now John has joined us to talk about some of the recent work his group at Surrey have got up to, looking at the bonding between organic and metal oxide materials. So John, over to you.
Great. Thank you very much, Robin. Well, as Robin mentioned in the introduction, I'm going to talk about the interaction of organics with metal oxides. That's something we've been concentrating on at Surrey for probably more years than I care to remember. And it's the core reason for doing it is to understand the adhesion of organics to metals. And what we're going to talk about is look at just a few spectra, which are part of a much wider ranging project about the interaction of a interesting organic molecule, a polymerized molecule, methylene diphenyl diisocyanate, with tantalum. And I'll explain, hopefully, why we're interested in tantalum. So first, let's say a little bit about the isocyanate. Isocyanate is a key component of polyurethane. We're all familiar with polyurethanes. They crop up as paints, adhesives. You probably drove to work sitting on a polyurethane foam in your car. It's used in coatings for furniture, also adhesives for furniture. Insulation, expanded polyurethane rigid foam is used in insulation. And of course, my interest is where we use polyurethane as adhesives. So polyurethane-based adhesives have excellent adhesion to metal oxide surfaces. And we've been trying to understand this working with one of the major manufacturers of isocyanate materials, Huntsman Polyurethanes, for about 12, 14 years now. And our particular interest, and the thing that we've been tasked to investigate by Huntsman, is the nature of the specific bonds that form between an isocyanate component of the polyurethane and the metal oxide on the metal substrate, be it aluminium, stainless steel, iron, nickel, whatever. So this is really what we're about, and this is what we're going to talk about this afternoon. So let's say a little bit about polyurethane chemistry, shall we? Polyurethanes are made from a diisocyanate with a diol to form this polyurethane, which has a soft segment part and a hard segment. So any polyurethane will have these two hard and soft segments. The one that we're interested in goes by the wonderful name of methylene diphenyl diisocyanate. That's a bit of a mouthful. Students that work on this always find it a bit difficult to get their head around what it means, but it's actually very easy. In the center here, we have a methylene group, methylene, diphenyl, so two phenyl rings, and diisocyanate. The work that we're going to talk about this afternoon deals with the polymerized version of this, and essentially a polymerized version of MDI is polymerized through a methylene group with the isocyanate group being associated with the benzene ring there, with the phenyl group. So what do we know about this already? What is known about the interaction of these isocyanates with metals? Well, fortuitously, quite a bit, and a lot of it has come from us over the years. And we've identified really two major interactions, one via the carbon in the isocyanate molecule and one via the nitrogen. So if we look on the left-hand side of the screen, we can see there M representing the metal with an oxygen interacting via the carbon in the isocyanate group of the organic material. And this could be described as a carbonate or a urethane bond. We first suggested that this type of bond might be forming back in the late 1980s. More recently, we've confirmed that with a publication that came out in an Adhesion journal last year. So one particular interaction that we might see between isocyanates and metal is this urethane-carbonate type bond. The other one is rather interesting and was quite a surprise to us when we first started thinking that it might exist. This is via the nitrogen in the isocyanate group directly interacting with the metal, as we can see there. And we don't really know exactly what to call this, but for the working title is it's a nitride-like bond, because there'll be electron donation from the metal towards the nitrogen there. And as you can see, we talked about that in a recent publication, and also a recent PhD thesis from my group discussed that as well. So why are we worrying about tantalum? Now, that's very a key point for this particular work. As I said, when we started working with Huntsman with their research centre in Everberg in Belgium, what we were doing was looking at the nature of the interactions that gave rise to adhesion. More recently, over the last sort of 4 or 5 years, we've been looking at, we've been working with the manufacturing plant in Rotterdam and worrying to a certain extent about not adhesion as a good thing, but as adhesion as a bad thing. So the fouling in the chemical plant that is used to make this methylene diphenyl diisocyanate. And the reason that we're interested in tantalum is there are certain parts of the chemical plant where actually taking the plant apart and cleaning it and removing the fouling is an incredibly expensive business. In more inaccessible parts of the plant, it's actually much better to think about putting a different type of material interacting with the reaction products. And one of the candidates is tantalum. So we were asked to look at the way in which tantalum might interact with the polymeric MDI material. And the way we do this is using a method that we developed some 25 years ago. We put down a very, very thin layer of the organic on the metal oxide, typically from a 10 to the minus 3 volume by volume % solution. And this will give us typically about 2 nanometers of an organic layer. We can then use XPS to interrogate both the bulk, if you like, of that 2 nanometers, but also the interface chemistry that exists between the metal oxide and the polymer. So we looked at 2 sets of conditions. We looked at a very thin layer from this 10 to the minus 3 V by V % solution that was just dried in air for several days, and also one where it was cured at 200 degrees centigrade. And these are the spectra that we see. And there's the tantalum 4F. And of course, the tantalum 4F is what we normally like to work with. And there's a minor oxygen peak that sits underneath the oxygen 2S. So we thought, well, let's not worry about looking at the tantalum 4F. Let's look at the tantalum 4P 3x2, which we duly did. And it sits exactly coincident with the nitrogen 1S spectrum. So this is in a way a good thing and in a way a bad thing, because it means that the analysis depth of the tantalum and the nitrogen information, because the electrons are of the same kinetic energy, is coming from the same depth. However, we've got to do some very, very careful peak fitting. Another thing I should mention as a sort of a by the by, we can see that our dried layer has quite a thin carbonate, and if we go away and calculate it using the Beer-Lambert approach, it turns out to be about 1.7 nanometers. If we actually look at the cured layer, it's a much thicker layer at about 3.5 nanometers. Once again, that provides us with some useful information about a slightly thicker layer, how that compares with this one. But of course, there's the uncertainties why we have different layers. The decision was made just to deal with this tantalum 4p3x2 peak, which sits coincident with the nitrogen 1s. We've done all our careful peak fitting around there. The driving force was to make sure that we could deal with both the nitrogen chemistry and the tantalum chemistry from the same depth in the same spectrum. On the screen now, we've got on the left-hand side a tantalum 4F spectrum of our tantalum foil sample, and we can see that the oxide is fairly thick. The spin orbit splitting of the 4F is very clear. The peaks are really quite slim, very intense because the cross-section of the 4Fs is very high. If we now go and look at our tantalum 4p3x2 of the same sample, so this is just metallic tantalum after it's been cleaned in a UV ozone cleaner, hopefully removing most of the hydrocarbon contamination. This is the tantalum 4p3x2 peak. There's metallic tantalum and 3 oxidation states of the tantalum oxide, 2, 4 and 5. And we can see that the ratio is rather different to what we're seeing in the tantalum 4F. So that gave us a bit of confidence that peak fitting the tantalum 4P was the right thing to do. If we take fresh polymeric MDI, smear it onto a piece of aluminium, we don't dry it, we don't cure it, we put it straight into the XPS spectrometer, we get a peak that we can see on the right hand side there. It's a very symmetrical peak representing the nitrogen in the urethane group that we have in PMDI. So how do we deal with this in actuality? So we're now thinking about our 2 tantalum specimens, both with a very thin layer of PMDI on them. One has been dried at 20 degrees, one has been cured at 200 degrees C. And as we saw from the XPS survey spectra, the thing that dominates the cured one is this component here, which is the isocyanate peak. We can see a couple of contributions there from the very weak tantalum peak. So essentially, our 3.5 nanometers of PMDI is all but obliterating the characteristic tantalum 4p3x2 spectrum. However, if we go and look at the one that's been dried where the layer is much, much thinner, we can see we've got the 2 tantalum peaks again, only much clearer this time, and we've got a lot of minor components in here. There are 2 minor components that are going to be very important to us. It's this peak here, which is at a very low binding energy, just above 396 electron volts, and that's what we've chosen to call a nitride-like component. And that's going to be indicative of a tantalum to PMDI interaction. There's also another component, which is this magenta line here. And this is nitrogen with a slight positive charge. And we think that's indicative of a donor-acceptor interaction. We can see it's here, only it's much, much weaker. But in the cured one, because of the thicker overlayer, we don't see any evidence of the nitride-like component. So the question arises, what is bringing about that slight delta positive charge on nitrogen? And we think we've got the answer by looking at thick layers of PMDI on tantalum. This was a 10% solution that was small aliquot, was dropped onto the tantalum, and it was then either dried or cured. Here are the XPS survey spectra. We can see carbon, nitrogen, oxygen, as we'd expect from the isocyanate material. Bit of silicon there, that's probably our old friend polydimethylsiloxane. I would like to blame my colleagues that used the oven that we cured it in for this, because it's not there on the sample that's just been dried in our lab. We go to a lab where there's an oven for curing composites, and what do we see? Polydimethylsiloxane, PDMS is ubiquitous amongst the compositors, so that's where we think that came from. If we look at the cured film first, we've got our isocyanate peak here. Now this is the peak that we saw on the PMDI that was immediately introduced into the spectrometer, only there was no broadening to either side. Now we've got some broadening, which is a carbodiimide material. This is a result of an interaction between 2 diisocyanate groups. It's well documented, we often see it, so that's no surprise. But we've also got this nitrogen with a slight positive charge on it over there. If we look at the dried spectrum, we can see very little difference in terms of the energies, but the intensities are much reduced. And what we can draw from this is that any reaction product within the PMDI itself is going to be enhanced by curing at 200 degrees C. So we see a little bit by drying, a bit more by curing. So how do we explain the nitrogen delta positive? With this thick overlayer, it's clearly nothing to do with an interaction between the PMDI and the tantalum, because we're not seeing any evidence of tantalum in the spectrum. But actually, this is just donor-acceptor or acid-base interactions, and it's the self-association of the isocyanate molecules themselves. And what we've got to bear in mind here is the relative intensity of the isocyanate peak with this peak. And this is really a very minor component. It might be of the order of 10% in intensity. But if you cast your mind back to the nitrogen component where we saw this, and we saw some isocyanate along with the tantalum, very thin film, this was about 40, 50, maybe 60% of the intensity of the isocyanate group. So the way we interpret this is the nitrogen delta plus is there as a result of self-association in the PMDI itself, but it's also indicative of donor-acceptor, sometimes called acid-base interactions, between the tantalum oxide and the PMDI. So let's try and draw this together and see what we've learned in the last few minutes. Self-association by donor-acceptor interactions is very limited in the dried layer, and it's only slightly increased when we cure the thicker layer at 200 degrees C. This spectroscopic feature, this nitrogen delta plus, that is assigned to self-association of the PMDI molecule, is also diagnostic of a donor-acceptor interaction between the PMDI and the tantalum substrate. For the very thin films, this component is a significant proportion of the nitrogen 1s intensity, whereas for the thicker films, it's a very low proportion. So we have this donor-acceptor interaction, acid-base interaction. We also have this nitride-like bond formation. And this is something that we perhaps feel a little bit more comfortable with. There's a interaction between the isocyanate group of the PMDI and the tantalum oxide in the way that we've identified for iron, chromium, and other metals. So we think we're seeing this sort of bond. There's a reaction mechanism there that I drew up last year or the year before, including iron, but if we replace the iron by tantalum, that's the reaction mechanism that we think we'll see. So that really sort of concludes a very brief canter through the story of an isocyanate material interacting with the tantalum substrate.
John, thanks for a very interesting presentation. The peak fitting you showed was quite complex. Do you have any tips for peak fitting strategies for these type of systems?
Yeah, certainly. What I always tell my students is anybody can peak fit a spectrum to get a good goodness of fit parameter. Any tool can do that, whether it's a chi-squared, reduced chi-squared, whatever it is, that is very, very straightforward. What one has to do is gather information. Now, the problem that we had with this particular spectrum at about 400 was there is nothing in the literature on tantalum 4p 3x2 whatsoever. So we had to look at our own tantalum 4p data and actually go away and collect a lot of it, especially for this particular piece of work, from both thick tantalum pentoxide films and our thinner oxides on metallic tantalum. And also, I think the thing that really informed what we've talked about this afternoon was the fact that we've done a lot of work looking at the fine structure in the nitrogen peak that involves an isocyanate. So we can recognize what the isocyanate component looks like. We can recognize if we see a broadening to a lower binding energy, that looks like it's involving the nitrogen in some sort of formal interaction. If we see a slightly higher binding energy peak, that's something that's a nitrogen with a slightly bigger charge. One thing that I should add is the schematic that I showed early on in the slide pack talked about an interaction via the carbon of the isocyanate group, and we really don't see that with tantalum. We've seen it with iron and also I think with chromium, and there that relies on very, very careful peak fitting of the carbon 1s line. And we've done very, very careful peak fitting of the carbon 1s line, and there's no evidence that we're forming that isocyanate or carbonate component. So yeah, it really is, one has to look very, very carefully at what's in the literature. One has to look very carefully at what one has acquired on a similar system in one's own lab. And then one needs to do peak fitting on similar specimens and look for consistency. That's really important. So although it's dead easy to do peak fitting and get a nice good value in terms of reduced chi-squared, that is one of the most difficult peak fitting examples we've done in recent years. And that was because nobody really knew about the tantalum 4PP, which was it was a challenge.
Have you tried depth profiling the thick layers? If so, does the structure look like the thin layer as you approach the interface?
Well, I'll respond to that with, that's a very good question, Robin, and there is a cautionary tale here. The cautionary tale is that when a researcher acquires their spectra, they should review them as they're being acquired and develop their experimental protocol while the specimen is still in the spectrometer. We didn't find out about this until we reviewed the spectra, or I suppose it was me that reviewed the spectra, and that's what we should have done. You're absolutely right. And by the time we actually took the specimen out, it had been around in the lab for a week or so. We put it back in the spectrometer intending to do that. And it had clearly changed, leaving it around in the lab a little bit longer. There'd been all sorts of junk absorbing on the surface, and we just never got round to preparing another specimen. So that's what we should have done. I mean, we should have done some cluster-fine profiling, and that's what we still plan to do. But we haven't got around to doing it yet. So yeah, and I think once again, it's nice to pull out sort of clear messages here. When you're recording XPS data, look at the spectra, particularly look at the survey scan. What does it tell you? And then don't feel that you have to keep too rigidly to the acquisition strategy that you decided before you'd seen the survey spectrum. If necessary, improve it a bit. And if I'd been in the lab, we'd probably have done some better depth profiling. But I wasn't, because I'm not often in the lab these days.
You mentioned in the presentation there was more carbon found on the cured sample, but not the air-dried sample, and you could see that in the rising background on your survey spectrum. Do you have a feel for why this might have been?
That was something that puzzled us, because it's counterintuitive. What one would think is that as you put your PMDI into an oven at 200 degrees C, the low molecular weight stuff, the oligomeric material, would be driven off and you'd end up with a thinner coating. That doesn't seem to happen, and we've talked about this amongst the sort of supervisory team with the guys at Huntsman, and the only possible explanation we can say is that as the PMDI that is dried in air is slowly drying, the loosely bound stuff, also the low molecular weight stuff, the oligomeric stuff, can just drift off into the atmosphere. Whereas when you actually put that layer into an oven, the thermal energy that's added to the polymer layer switches on all the cross-linking, and even the low molecular weight stuff is cross-linked into the system. I have to say it's not something we've seen before, and we've worked with PMDI on quite a bit over the years. But I think that's the only explanation we've come up with that passes muster, both from a surface analysis perspective and one that the isocyanate experts, the people who know isocyanate chemistry much better than I, that they're comfortable with as well. So that's the interpretation we put on it. And it is only an interpretation. We can't be absolutely sure.
Well, John, thanks again. Where can people find out more about your work or your group's work?
If you go to the University of Surrey website, which unsurprisingly is www.surrey.ac.uk, and just put a search in for John Watts, that'll take you to my website and my group's website, and that will explain a little bit more about the isocyanate work we've done over the years, but also a bit more about the other materials related research that we're carrying out with surface analysis methods. Anybody that would like to email me is absolutely welcome to do so. So that's j.watts@surrey.ac.uk. And before we go, I have to plug the best introductory text in surface analysis. It was published earlier this year. This is by myself and John Wolstenholme. And I have to thank Robin for doing the graphics on the front cover, which are excellent. So if you don't like the graphics, it's Robin's fault. If you do like the graphics, I really made a good choice. Thanks very much, everybody.
Thanks, John. Thanks. Bye now.
Bye-bye.
Thanks for joining us for our interview with John Watts. We hope you found it as interesting and informative as we did. If you want to see more content like this, you can visit our website at xpssimplified.com. There you'll find webinars on demand, app notes, and other resources like our new multi-technique infographic, as well as many other videos like this one and information about our XPS and surface analysis products. Remember to look out for our next interview, where we'll be talking to Dr. Damien Aurel from the University of Versailles.